about this yesterday. Arithmetic sequences behave like what type of functions? Linear. Whenever we're talking about arithmetic sequences, our a sub n, right, whenever we're talking about arithmetic sequence, this is our general term, or we could call it the nth term. A sub 0, this is our initial value, and our D is our common difference there. So we filled those things in yesterday. Today we're going to be looking more at linear functions and how they relate. So in a linear function, your f of x is just your output for whatever term you have for your x. B, when we're talking about linear functions, we usually call that our y-intercept. And m is our slope, or sometimes we'll call it the rate of change. Those would refer to the same things. And so you can sort of see the parallel here. Whenever we're talking about sequences, our common difference is pretty much our slope, right? Our initial value is pretty much our y-intercept. That f of x sort of corresponds to our a sub n. What is the only difference, really, between our linear functions and our arithmetic sequences? Very good. Arithmetic is only points. The linear is all connected, right? Because for arithmetic sequences, we can only plug in whole numbers for that. Okay? So, we also are going to learn about a new form of linear functions that I don't believe you guys have done before. So yesterday, we wrote down this formula right here, right? So a sub n is still our general term, or our nth term. And a sub k is our, I'm going to call it the kth term. I don't know what you call it. That sounds wrong. But you can't do like second either. Yeah, it's got to be kth term. Maybe. Either way, that's going to be a number, right? It's going to be the 5th, the 7th, the 8th, something like that. The 2nd. Here. And that is your known term. So it's like, you know, if they give you the 2nd term or the 5th term or the 9th term. And D right here is still our common difference. So similar to that warm-up, we had different approaches to doing that warm-up, but if you did that warm-up, a sub 2 was 8, and the common difference was, what was it, 3 on that. So I could have used this formula where a sub n equals a sub k would be the 2nd term, that would be 8, plus the common difference, which is 3, and then n minus 2. Okay, so like that was an option. You are starting with 8, you need to add 3 however many times, and to decide how many times, you would do n minus 2 for that. Okay, we are going to compare this to this form right here. for a line. And when I was in high school, our math one, it was Algebra 1 then, but our Algebra 1 teachers taught us this form. Like, this is how we wrote equations of lines, pretty much all the time. And the first few years I also taught this form of a line. However, I have not taught this form of a line in Math 1 in a very long time. And I don't think most of our other teachers do, because what I was finding is that kids never remembered the formula. And then it did them no good if they couldn't remember the formula. And so there's a way you can do it from y equals mx plus b, and that is what we just used because kids remembered y equals mx plus b. However, I want to introduce this here for a couple reasons. Number one, it's very similar to this arithmetic sequence formula that we learned yesterday when we have that known term. And number two, this is very useful in calculus. I teach this, whenever we write equations of lines in calculus, we use this form every time because it makes it quicker to write the equation of a line than the way that you've been taught before. We tried to teach this in Math 1 because we'd be like, oh, kids need it for calculus. And then eventually we were like, wait, kids are not doing great with this. And the kids that make it to calculus, you can teach them how to do this in 20 minutes. I'm going to introduce it here. We're going to use it a little bit. When it gets to calculus, we'll use it even more here. But it's a fairly basic concept. If kids had the formula memorized, they could do it easily in Math 1. The problem was kids were not memorizing the formula whenever I used to teach it. So for this, f of x is just your output, which corresponds to that nth term. x1, y1 is a point on the line. And m is your slope. So let's look at how this would correspond to that warm-up problem that we had. If I've got the point a sub 2 equals 8, if I'm not using sequence notation anymore, that's like having f of 2 equals 8. And what does it tell us if f of 2 equals 8? What does that tell us about points on the graph? What point is that? That's the point 2, 8, right? And then we know that the common difference is 3 here. That corresponds to the slope being 3 over here. So what happens here is that 2 is our x1 and that 8 is our y1. So if we look at this formula here, you can use either one of these. I usually use the second one more in math, in calculus. It really doesn't matter. It's the only difference is whether you put the y1 at the front or the back, but it's just added so you can move it around wherever you want. Let's use that first one there. So I would say f of x equals y1, which is 8, plus m, which is the slope, times x does not get replaced, it stays there, minus y1, which is 2. Notice how these two formulas are almost identical right here. So this formula right here is sort of the function notation version of this other formula that we were using yesterday. This equation is called the point slope form of a line. Y equals mx plus b is called the slope intercept, because to do y equals mx plus b, you have to have the slope and the y-intercept. This is called point slope because you need a point on the line and the slope of the line to write that equation. So let's practice with this a little bit more. Okay, so we've got an equation of a line that has a slope of 2 and passes through the point for negative 8. This is a Math 1 problem. Here. They're not going to probably only ask you to do this. It'll probably be in conjunction with something else. But it's a Math 1 problem. I'm going to show you what you guys did in Math 1, and I'm going to show you how you can use point slope form for this. So in Math 1, we always started with y equals mx plus b. That's where we started from. All right. And then our m is 2, because they give us our slope. But do we have the y-intercept in this case? We do not, so we can't plug it in. So now we're looking at y equals 2x plus b. So what you're going to have to do is plug in to find the b. So I know this is my x-coordinate and this is my y-coordinate. So I could plug in -8 right here for the y. That 2 right there stays. I'm plugging in 4 for the x. Then I've got the plus b, which is what I'm trying to solve for. So I've got -8 equals 8 plus b. And I need to subtract 8 from both sides to get that b right there by itself. So -16 equals b. So m is 2, b is -16. So we could write the equation y equals 2x minus 16. Do you guys remember doing that? Is that might have been a while, but you remember doing it? Seems familiar. So this is usually how we teach it in Math 1. Point slope form I like to start using at this level because I'm going to rewrite point slope form here. Y equals, I usually do this version, m times x minus x1 plus y1. I usually put the y1 over at the end. You could technically put it at the front if you want. So in this case, my m is still 2. And then my x1, y1 is 4, -8. So this is why I like to use this in calculus. You're going to plug things in. You've got y equals, m is 2. You do not replace the x, but you do replace the x1, which is your x-coordinate of your point. That's a 4 right there. And then your y1 coordinate is just added over here on the end. You're going to have plus -8, which is really just like -8 right there. Now, the reason that I use this right here in upper level math is you don't have to simplify that. You can leave it. You don't have to put it in y equals mx plus b form. You can type that into Desmos. It'll graph it just the same as it graphs 2x minus 16. And so we can stop, right? Much less work here. If you need slope-intercept form for some reason, like if they ask you for the y-intercept or something, all you're going to do is distribute that to 2x minus 8 minus 8, and you get y equals 2x minus 16, right? So it's equivalent here. But you could stop right here at this point. So I use this in calculus because there's a lot less room for error. As long as you have that formula memorized, a lot less room for error, right? So I would encourage you to memorize this formula because not only does this take longer, it also, like right here, if you accidentally add that 8 instead of subtract the 8, you're going to get a 0 for your b, and you'll be wrong there. Whereas right here, you don't actually have to do any calculations for it. So that's the difference between like our two forms that we're using here. Questions? All right. Let's talk about some geometric sequences. Geometric sequences are going to behave like exponential functions. And so our G sub n here is our nth term, or our general term. G sub 0 is still our initial value. And our R is our common ratio. Okay, this directly mirrors what we will see in the exponential function. So exponential functions here that you learned in Math 1, f of x here is just your output that you get whenever you plug in whatever x is. A is going to be your initial amount. It is what you get when you plug in 0 for your x. And B is going to be our growth or decay factor. And so you can see that these, correspond to each other here. Just sort of different notation. The only difference is on sequences we can only plug in whole numbers for that. All right, now let's look at that more complicated version. So sometimes we don't have G sub 0. We've got G sub k instead. So if we have G sub k, then G sub n is still our nth term or our general term. K is our kth term, or G sub k, sorry, our kth term, or we can think about that as our known term. And R still our common ratio here. Whereas over here, f of x will be our output. X1, y1 is going to be a point on the curve. I want to call it a curve instead of a line because, of course, exponentials are not straight lines. And B is that growth or decay factor. So I'm going to do we didn't do one of these on the warm-up, but let's do one similar here. So, let's say that I knew that A sub 3 equals 4, and that my common ratio is 2. So I think these are a little more confusing. So I'm going to, I've got, I don't really want a table. I'll erase all those. If I've got, I know A sub 3 is 4, right? So if I want A sub 4, I would need to multiply by my common ratio, which would be 2. So I get 8, right? And A sub 5 would be 16. And A sub 6 would be 32, right? So that's what's happening each time. So if I want to write this as a formula, my A sub n is going to be the term that you know, the 4, times the common ratio, which is 2, But, so like if I'm trying to get to the sixth term, I would multiply by 2. Like, let's just say I'm trying to get like a sub 6. Oh, I was hoping somebody was coming. I saw y'all walking down the hall. Thank you. So, like if I know that a sub 3 is 4, and I'm trying to get a sub 6, right? I got to multiply by 2. 1, 2, 3 times, right? That's because I had to do 6 minus 3 because I started at the third term, not the 0 term. So I got to do n minus 3 right there. Okay, here's what it's going to look like if you're dealing with a, here's what it's going to look like if you're dealing with a function instead of a equation right here. You're going to have a point on the curve. So instead of getting a sub 3 equals 4, you'll get f of 3 equals 4, which tells you what point? 3, 4, right? And then your b value, which is your common ratio, would be 2 here. So look at our formula here. F of x is going to be the y coordinate that we start with, right? Then we have to multiply that by 2. And then we'll have x minus the x coordinate. I like to think of that table, right? I know that if I plug in 3, I get 4. If I plug in 4, I would get 8. If I plug in 5, I would get 16. Plug in 6, I'd get 32, right? So by subtracting that 3 there, since you're not starting with the initial term, that adjusts for not multiplying by 2 as many times. And I'm going to flip ahead to remind myself whether I showed you how to simplify that or whether I want to. I think we're going to talk about simplifying those later. We're going to stop. We're not going to change those right now. We'll probably need to look at it though. All right. So here's some ways that they like to talk about these. Okay. So we've got to be able to talk about rates of change in linear and exponential functions. So we have seen this language before, right? Over equal length input value intervals, the output values change at a blank blank here. So think about a linear function. Let's do a really easy one. Like let's say we've got 0, 1, 2, 3, and let's say we got 4, 6, 8, 10, right? So if we're talking about the rates of change here, we first have to check that we have equal length input value intervals. What does that mean when we have equal length input value intervals? In what? If we're only talking about the input values, those are which values? The x values. So we're wanting to look at the input values are x values. We want to make sure the input values are going up by the same amount each time, right? So 0, 1, 2, 3. We're increasing by 1 each time. Then we would look here at what's happening to the output values, or the y values. And we can see we're going up by 2, up by 2, up by 2. And what do we call that whenever our output values are changing at the same rate each time? Constant rate. Okay. Now, linear functions are like arithmetic sequences. The change m in y is based on addition. Sometimes it looks like subtraction if you're like adding a negative number, but addition, here, we're adding 2 each time. Okay, let's think about an exponential function. Okay, so for exponential function, I'm going to do the same thing, 0, 1, 2, 3. Okay, an exponential function might be something like this, like we start with a 3 right here, and then we get a 6, and then a 12, and then a 24. Okay, so if I think about what's happening here, now I can see, hopefully, what I'm doing each time, right? What am I doing to get from 3 to 6 and then 6 to 12 and 12 to 24? I'm multiplying by 2, right? In fact, if we want to fill in this, the change b in y is based on multiplication. Right here. But if I think about like looking at the rates of change, right, just looking at slope, then this went up 3 and up 6 and up 12. Now here's the interesting thing. What if I do it again? Up 3, up 6. If I do it again, up 3. So, like, and if I had more numbers here, like, let me put a few more. 48, 5 would be 96. So this goes up 24. This goes up 48. So, like, from 12, this is up 12. This is up 24. Up 6. Up 12. I'm running out of room right there. Like, you'll see this is never going to be quadratic, cubic. You know, whenever we were doing this for quadratics and cubics, we were seeing that we'd get, eventually we would get a number that was constant, right? That's never going to happen with exponentials. What's happening is that things are changing proportionately, right? So we're going to say proportionately. I don't know if there's an E there. I think there's not. Okay, that means it's based on a percentage, right? Like think about, you know, like you can think of a lot of things proportionately, right? If I lose $20, I'm going to be sad about that. If Elon Musk loses $20, he probably doesn't even realize he's lost $20, right? Like, proportionately, $20 is a lot more to me than it is to Elon Musk. You're thinking percentage-wise, right? $20 out of my total money is a lot more than $20 out of a much bigger total, right? So what we're seeing here is that the next number is like a proportion, right? It's percentages that we're looking at, not straight addition for that. I'm forgetting what goes in those blanks right there. It's okay. I think that I've done this in case I do this. Oh, yeah. If you have 2 points. So glad I decided to do that. That was a good trick right there. Everything else I had there went away. But if you have 2 points, oh gosh. Then you can write linear or exponential functions. You have enough information to write linear or exponential functions, or arithmetic or geometric sequences, because they correspond. So let's look at tables. If we are trying to decide whether a function is linear, exponential, or neither, the first thing that we have to check is that we have consecutive equal length input value intervals, right? That just means that x is going up by the same amount each time. So if I look at all of my x values, do I have consecutive equal length input value intervals for all these tables? They're not all the same, but are my x values going up by the same amount within one table? Like here, this goes up by 3. This goes up by 3. Up by 3. Again, up by 3. Right, so that's the only requirement, right? So as long as within that one table, our x's are going up by the same amount, we can look at what's happening to our y values. So down 2, down 2, down 2, down 2. What do I have here? Linear. Okay, we've already talked about those, right? We did that when we were doing quadratics and cubics as well. But if I look at 3, I have consecutive equal input value intervals. This goes up 1, up 3, up 5, up 7. If I do this again, that's up 2, up 2, up 2. Is this one linear? Is it exponential? No, what is it? Quadratic. So we would say neither here, but because we're also remembering what we have already learned from Unit 1, we know this one's quadratic. On the next one, let's look at what's happening. Up 1, up 2, up 4, up 8. Now, you also can kind of look and see, oh, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. Like you can see, oh, that's exponential. I'm multiplying each time, right? But if you're looking at the addition, look at what happens. I got up 1, up 2, up 4. It's just like the same pattern over again, right? And then if you do it again, up 1, up 2. This is exponential. Let's look at one where we are decreasing, right? So equal length input value intervals, we're going up by 5 for our x's. So we can say this is down 40, down 20, down 10, down 5. Right, definitely not linear. If I do it again, I get down 20, down 10, down 5, down 10, down 5. Yes. Oh, you're right. On that next, up 20, up 10, up 5. And then down 10, down 5 on the next. Yes, because we're with negative numbers there. So I do see like a switch from positives to negatives there, right? But do I see a linear or quadratic or cubic pattern? I do not. And is there a number I can multiply by that would give me each one of these successive terms? I can multiply by 1/2, right? And that would work. So this one is also exponential. Because you're looking at one that's decreasing here, you may see those negatives switch back and forth. If you're silly like me, you may have missed that these are like 20, 10, 5 right here, because going from negative 40 to negative 20 is actually up 20 right there. But this still shows an exponential pattern right there. Does that make sense? Okay. All right. So we'll need to be able to identify those. Let's look at some word problems for these. So a large theater has rows of seats where the number of seats in each row can be modeled by arithmetic sequence. In the fifth row, if the fifth row has 31 seats, that's telling me A sub 3 equals 31. And the 11th row, A sub 11, has 49 seats. determine how many seats there are in the 25th row. Now, I find it very helpful to think of this more as a function than a more of it as a function than the like arithmetic sequences. So arithmetic sequence, when I see that arithmetic, that tells me this is like a line, which means there's a slope, right? I have a common difference, which is a slope. So this is really like the point 331. Yes, I do not know why I had a 3 there. Let's turn that to a 5. So I've got 531, and I've got the point 1149. And if I want to know the common difference here, common difference is the same as slope, I could just find the slope. So my slope formula, remember, is y2 minus y1 over x2 minus x1. You don't have to necessarily write it down, but I'm just reminding you if you've forgotten. So we would do 49 minus 31 over 11 minus 5, which is going to give me, let's see, 18 over 6, which is 3. Now, we don't have our a sub 0, right? A sub 0 is like your y-intercept. But we could use that formula that we use, that point slope formula, or I'm going to go ahead, I mean, you can use a sub n if you want, I guess. A sub n equals, I could use either one of these points, right? So if I'm using that other formula, I could use 531 or I could use 1149. It does not matter which one you pick, you're going to get the same answer. So I'm going to use 531. So I would have my 31 is the number of seats in that 5th row. Plus, I know I'm adding 3 seats each row. That's my slope. That's my common difference. And then I would need to do n minus 5 because I didn't start in the initial row. I started in the 5th row. Right? So if I want to know a sub 25, I could do 31 plus 3 times 25 minus 5. And a sub 25 is going to be 31 plus 3 times 20, which is going to be 31 plus 60, which is 91 seats. There are other ways to get the answer here. I mean, you could start at 11 and just add 3 until you get to 25. But this is going to be a little bit quicker if we rely on that sort of point slope form. All right, I know we got 3 minutes. Let's try our best to get this last one right here in. A wild rumor is spreading. The number of people that have heard the rumor can be modeled using a geometric sequence, where 43 people had heard the rumor on day 3. So G sub 3 equals 43, or we can think of that as the point 343. And on day 6, 140 people have heard the rumor. So G sub 6 equals 140. So we've got 6, 140. I don't have time to do this. I'm going to stop. I'm going to have to rush through it too much. It's not going to make sense. We'll skip that problem on the homework and then